Alright, so hello everyone. So in this particular video lesson that we will going to have today is we will going to discuss something that is more profound as what Alfred Wegener haven't answered yet. Okay, so since we are done already with the direction and rates of plate motion, so in the previous video we have discussed how is this one possible and what are the techniques that are used in order to find the relative movement or the rate of motion of every plate. So in this video lesson that we will have today, we will going to discuss what drives the plate motion. So as 100 years ago, Alfred Wegener didn't manage to find the answer to this question. So if you will think further, it is impossible to move gigantic continents with just a drift of waves of water. Right? So that is why his continental drift hypothesis was rejected. Okay. So in this lesson that we have right here, so we are going to find out what are these forces that is necessary to drive the plate in motion. Alright, so there are several driving mechanisms of plate motion. Okay, one of them is there are a lot of models that explain, but none of the models somehow manage to explain accurately how the plate motion works. But there are some speculations and there are some hypothetical models that are used in order to explain this plate motion that we have. All right, next one is one causes of plate motion is the Earth's heat itself. All right, so the Earth's heat is the driving force that enables the plate to move. All right, so if the Earth's heat is the driving force, so how is it possible? Great. Next one, these are the models that are produced that is said to be connected to the motion of the plates. So the first one is the slab pull, the other one is the slab push. Alright, so how does these two become different for each other? Alright, so by the way, before we go to the mechanics itself, alright, let's recall that force, the definition of force is a push or a pull. Alright, so this is an instance where you push something or an object, and this is an instance also when you pull something. Alright, so in that case you pull you pull that particular object. Alright, you push or a pull. So when you do those two motions that you have right there, therefore you are doing force. Alright, so in slab pull, the descending oceanic crust pulls the plate downward. It goes to say that gravitational pull has something to do in this particular process that we have right here, this one. Alright, so gravitational pull. So next one, the ridge system, which is located at the divergent boundaries. These are some places that pulls, or that rather pushes the plate away from each other. So when there's something that push, there is a place where a plate is pulled downward. So we have here the subduction zone. Okay, basically the one that is described here is the subduction zone, and the elevated ridge that we have right here is the spreading ridges the statement is talking about. Alright, so spreading ridges. Alright, so because of these two systems that we have right here, there is a tendency that a plate will move. Alright, so basically, what Alfred Wegener didn't manage to find out is that the driving force in which your plate moves is just a simple push and pull motion of the plates. Alright, so this is the driving mechanism. So if you will going to look at analogy for this one, so we can safely say that it looks like a something like a baggage counter in an airport, so in which the baggage sits on this moving escalator like or something like panel over here, a moving panel over here, and it circulates as the owner approaches his or her baggage. So this baggage will circulate and will ride along this panel as it moves. Alright? So we can safely say that the plate motion is just like this. Alright? Or if you take a look at a treadmill, if you manage to sit yourself there, so the movement of the treadmill enables you to move as well. Alright? So you follow the motion of your treadmill. Okay, so this is one example, this is one analogy of what I'm talking about. Alright, so this is the picture of this two mechanism or two forces that we have right here. Okay, so in this area, we call this one the subduction zone. The dominant force here is the pulling force. Alright, so what kind of force does pulling? So we can say on this particular part and the subduction part, gravity helps this particular process. Okay, so the gravity pulls this oceanic plate here that we have right here, this lithosperic plate that we have right here. Because of the action of gravity, the lithosperic plate over here goes back to the mantle. Meanwhile, as it goes back to the mantle, there are some materials that are brought upward coming from the mantle. And as it is brought upward, it pushes the plate away from each other. Alright, so where's that area possible? And that area is now, it is in the area called the ridge system. Alright, or basically in the divergent boundary. So the slab pull on the subduction zone, mainly this subduction zone is found in the convergent boundary, and the ridge system is found on the divergent boundary. So these two forces that we have right here enables, drives the plate motion that Alfred didn't manage to find out. Alright, so next. Okay. Now in this particular topic, so we will going to look forward on what are the models that are proposed by some geologists on which they think the things that drives the plate motion. Alright, so basically how the convection cycle looks like under the Earth, or what does a convection cycle looks like under different layers of the Earth. Alright, so in this particular topic, so it will explain how mantle plume, alright, be able to extend from core mantle boundary, and this mantle plumes somehow causes this convection movement. So what do you mean by convection? Convection is a transfer of heat in a fluid. Alright? So, and also convection depends on the density of your fluid. So if the fluid is heated, it expands more. Alright? It expands more and it becomes denser. Alright? And rather less dense. Then when the fluid becomes cooler, it compresses itself and it becomes denser. So what is happening here, because of the process called convection, it allows the fluid to transfer heat coming from the core down to the mantle, and because of this movement of your mantle, it drives the lithosperic plate that sits above this mantle that we have right here. And the push and pull system that we talked about earlier is possible only if there is what they call convection, the mantle convection. Alright, so there are several models that are proposed. So we have here the layer at 660 kilometers. We have the whole mantle convection, and we have the deep layer model. Alright, so just to view what is a convection looks like. So if we take a look at this plate motion that we have right here, so this pattern of movement, this arrow that we have right here, this movement of fluid is caused by convection. So once once fluid cools down, it becomes more denser and then it goes back again to the bottom, and those material that are heated goes up because they become less dense, and the cycle continues. So there are two cycles over here, and the one at the middle, and the other one will go to the other side. So the convection continues because there is a heat coming from the Earth's core. Okay, so let's discuss these different models that we have right here. And just a disclaimer, none of these models, or some of the models that we have right here that we were going to discuss have shortcomings. And upon the discussion, I will just talk about, or I will just tell you what are the shortcomings of each model. That is why none of these models somehow followed in terms of how the plate moves. Alright, so next one. Alright, layering at 660 kilometers. Alright, so as you can see from the word itself, layering, so meaning to say that the convection, according to some geologists, that the convection pattern that is happening inside the Earth happens at different layers of the Earth. Alright, so there is a convection pattern happening on the upper mantle, there's a convection pattern that is happening on the lower mantle, and because of this layering, there are separation of heat transfer between two layers. Alright, so for example, this movement, the movement of fluid over here on the upper mantle. So as this fluid moves towards this direction, so the plate above it will move also towards that direction. Alright, so as you can see here, you can see some subducting or subduction zone. And once that particular plate, that lithosperic plate subducts, it goes to the upper mantle only. So as you can see, this particular material coming from that subduction zone doesn't go to the lower mantle. So it stays on the upper mantle itself. Okay, so this is what layering at 60 kilometers looks like. Now, what is the shortcoming of this? Model? So the shortcoming of this model is that, right? So let's talk about first the advantage. Right. So the advantage of this model, it explains why hotspot volcanoes have different chemical composition of rocks than the one found on the volcanoes found in the ridges and also on the subduction zone. Alright, so because of this particular model, it explains why the rocks in the hotspot volcano is different from the rocks coming out from the plate boundaries, just like the one in the ocean ridge and the one on the subduction zone. Alright, now what's the shortcomings of this model? Now, using the seismic data from an earthquake, so based on that data, it is inaccurately measured that around 660 kilometers, the convection likely to happen. So according to some geologists, and according to that seismic data, 660 kilometers is somehow an inaccurate distance upon each layer. Right? So that's the shortcoming of this. But if you think of its finding, we can safely say that somehow this particular type of convection pattern somehow is present in our Earth's layer. Alright, so that is layering at 660 kilometers. Alright, next one is the whole mantle convection. Now, in the whole mantle convection, right, the difference of this one in the layering is that the whole mantle itself. So as you can see, this convection or the movement of the fluid coming from the core. So the core will hit the fluid and then the fluid becomes less dense and then it will cool down and it became more dense and so on and then so forth. So the whole mantle itself is moving, right? So what are the other things that we can see here? We can see here that the subducted material from the subducted lithospheric plates, instead of going only from the upper mantle, it goes directly going back to the lower mantle. Right? So it goes back to the lower mantle and the cycle continues. Alright, and in this whole mantle convection, it explains that the mantle plume is the one, that the mantle plume itself, the heat coming from the mantle plume is the one that triggers this convection pattern that we have over here. Okay, so as you can see here, another mantle plume on this side, thus producing a hotspot volcano on that particular area. And this mantle plume, this heat coming from the mantle plume drives the convection pattern, over this particular region of the in the layer of the Earth. All right. So let's talk about its advantage. All right. So the advantage of this one, it explains how. All right. It explains where does the subducted lithosphere will go. Alright, so in this particular type of model, as you can see here, the subducted plate goes back to the lower mantle. Okay, and it explains, and in this model also it explains how the mantle plume, what is the purpose of this mantle plume? Okay, that forms your hotspot. Okay, so the shortcoming of this one, model that we have right here is that it eliminates, alright, so this model eliminates the idea that the mantle or the plate boundary volcanoes have different rock composition than your hotspot volcano. So, meaning to say, as you can see here, so the subducting thrust or the subducting plates over here, whatever composition is this, will be brought out on this part. Okay, so meaning to say that the rocks coming out from the hotspot volcano is the same thing as the composition of the rocks going from the subduction zone and then goes back again to the hotspot. So meaning to say in this model, there is no difference between the rocks coming out from the hotspot and the rocks coming out from the plate boundary volcano. So, according to the geologists, that is impossible because in their observation, the rocks from the volcanoes is different from the rocks in the plate boundary volcanoes. All right. So the third one is the deep layer model. So the deep layer model is just a combination. This is just a combination of the two models that we have discussed a while ago. Alright, so there is a convection pattern on the upper and some parts of the lower mantle, and there is a convection pattern that is happening on the layer near the core interface that we have right here. Okay, and also this model explains the occurrences of your mantle plume. Okay, and also this particular model explains how hotspot volcano is formed, and also it enables us to give an idea that the subduction zone or the subducted lithosphere goes back again from, instead of having it on the upper mantle only, it goes to the as deep as the lower mantle. So in this deep layer model, this is just a hypothetical model. It explains that the one that goes out from the rocks that goes out from the hotspot volcano is somehow different from the volcanoes the rocks that goes out from the plate mantle boundaries, just like the oceanic ridge. Alright, so this particular model is still in study, so we haven't yet found some shortcomings of this model. So this is the recent model about the Earth's convection. Alright, the Earth's layer convection is somehow proposed as of now. Okay, so we have the deep layer model. Alright, so in summary, the plate tectonics is supported. Alright, so the plate tectonics, the movements of the plate tectonics is supported by the following ideas. Alright, so one is the ages of the sediments in the seafloor or the floors of the ocean basin. Next one is the existence of hotspot volcanoes Alright, and over the hotspot volcanoes, underneath the hotspot volcanoes, there is what they call the mantle plume, which is said to be stationary and long-lived, enabling us to detect how much the plate moves. Alright, and lastly, we have the paleomagnetic evidences suggest that the Earth's magnetic field somehow reversed, and this magnetic reversal can be traced in order to find out the relative motion of our plate. So there are three ways that supports the plate tectonic theory. Okay, and what we have discussed a while ago is that the mechanisms that contributes to the, or that is the product of the convective flow, which is present on the Earth's layer, is the slab pull and then the ridge push. Alright, so just take note, these are the two forces that drives the plate motion together. And these two forces is possible because of convection. Again, convection is the move or heat transfer in fluids. Alright, next, the process of convection is that the hot and buoyant mantle plumes are considered the upward flowing arms of the mantle convection. So, upon this, using this mantle plume, it drives the convection flow inside the different layers of the Earth. And there are three basic models that we have right here, just like what we discussed a while ago. We have the basic model, like layering 160 kilometers, full mantle convection, and the deep layer model. So none of this model has been confirmed yet because each model that we have right here has its shortcomings. Alright, so basically that's all about what drives the plate motion, and I hope you did learn something from this video. See you next time.